All right. Hi, everyone. We are the Volpe Santos scope team, and this is Project View. All right. So my name's Kristen Walker. This is Lucy, Liz, Rebecca, and Gabe, and we are sponsored by the Santos Family Foundation, which is an organization that works to improve road safety. We also had the pleasure of working with the Volpe Center as our technical liaisons as part of the U.S. Department of Transportation, and they're located over in Cambridge. So our project was to create an independent standard for measuring blind spots, as a standard doesn't exist for large, heavy good vehicles. So essentially we wanted to locate these blind spots. And the goal of that was to mitigate collisions between these vehicles, such as trucks, and vulnerable road users, such as pedestrians and cyclists, specifically in urban environments. So we purely looked at direct vision, and direct vision is anything that you can see with your eyes. So if you're looking through a window, that's your direct vision. So this photo on the left shows a truck that has these really large windows, and this driver can see those two people that are right there, whereas this truck on the right has smaller windows, and that driver is not able to see those two people without the aid of mirrors or sensors. And the reason that we looked at this is that research has shown that drivers with direct vision can react 0.7 seconds faster than drivers with indirect vision. So once we got into the project, our first thought was, okay, let's get some computer models or CAD of these trucks and see what we can do. Unfortunately, CAD of these trucks is proprietary information, and we were not able to get that. So we moved on and we said, well, how can we create our own CAD model? So we bought this camera called a Z, and we went around and scanned trucks with this camera. And the photo on the left, that's really terrible, is what we discovered that this could do. So it was a really low resolution, inaccurate model of the trucks that we were interested in, so it was unusable for us. So we moved on to using LiDAR, which is a distance detection device, and we wanted to look through the windows of these vehicles. And it turns out that when you do this through windows, the coding on the windows distorts all of your data. So moving forward, we decided to we left all the really high technology, and we've decided to make our own method, which is called the panoramic method. So essentially, we took this pole and we put 1 foot increments up the pole, and then placed a smartphone in the driver's seat at the driver's eyeballs, so kind of simulating what someone could see through a truck. And then with that camera, we took a panoramic photo looking out through the windows, and then used some image processing to quantify what the visibility of that photo was. So here's an example of one of the panoramic photos that we took. It's a little washed out in this photo, but there is a measurement pole directly in front of the vehicle, and this is theoretically what someone would be able to see if they were sitting in that driver's seat. So now onto what we did with that image. We did something called line propagation. So essentially we used that measurement pole as a scale, and so I know how far away that measurement pole is from the camera. It's 8 feet. And I know that that pink line is 6 feet high, so essentially anything that is 8 feet away from me should show up along that pink line in the photo. And what we did with that is we wanted to know what was the lowest visible height. So what point in that photo can I start to see my surroundings and no longer see the vehicle? So in this photo at 0 degrees, that yellow line is visible, which is around 4 feet. So if I were to put a child who was 2 feet tall, 8 feet away from me at that 0 marker, I wouldn't be able to see that child.
Right. So from these lowest visible heights along the measurement pole, we can use similar triangles to calculate the nearest visible point that the driver can see on the ground at each position around the vehicle. So this allows us to create a footprint of the blind area along the ground. You'll see an example up on the screen. This only has 5 points, but when we're actually calculating these, we generally are using over 200 points for each truck. So with these nearest visible points on this area map on the ground, we can draw a line from the points to the driver's eye position, or where the image was taken from. And the volume below these is blind, and the volume above these lines is visible to the driver. So what we're interested in giving users is the percentage of visible volume, which is the visible volume over the total volume. Now the total volume includes both the visible and blind volume out of the front and passenger side window near the cab. And this is because this area is where most collisions with pedestrians and cyclists occur. To actually calculate this percentage visible volume, we created a website, and this someone might use to assess the direct vision in their current fleet or to investigate a truck that they're considering purchasing. So first, the user will upload the image that they've taken. They'll mark each of the height marks along the measurement pole, and this calibrates each row of pixels with a height marker that's true at the radius of the measurement pole. Once they're done with that, they'll mark the 0 degree and 90 degree points. This allows us to calibrate each column of pixels with a degree relative to that 0. Once we're done calibrating the image, the user, as they're doing now, can draw in this orange line across the front where they can first see the ground out of the front window and passenger window. With this and a few extra measurements, we're able to calculate the percentage visible volume and give that back to the user. Users can then choose to upload a vehicle identification number, which will add their vehicle and all the vehicle's information to our database. So these are some examples of trucks that we have scanned. And this is really important because our method is comparative. It's not helpful to know what percentage visible volume your truck has if you don't know if it's better or worse than other trucks that you could have used instead. So anyone can look at this when they're considering which truck to add to their fleet. And here are some example results. The top truck is a cab over engine vehicle with a 71% visibility, and the bottom truck is a conventional cab with a 57% visibility. You'll notice in this top truck, the front window extends further down than in the bottom truck, and in the bottom truck, the nose of the cab obstructs some of the view that would otherwise be visible to the driver. We're really excited about our method. It's repeatable, low cost, and we've gotten a lot of interest from fleet managers, city safety officers, attorneys, insurance companies, and other researchers, even though our method is still in the prototype phase. We are writing a technical paper that we've submitted to the Transportation Research Board, and this will give our method additional credibility so that it can be used in this industry by both fleet managers and policymakers looking to make better decisions that include this important safety factor. We'd like to thank everyone that we worked with here at Olin College, Jason and Oliver, at Volpe, Margot and Alex, the Santos Family Foundation, Paul and Ann, and at the City of Boston, Scott and Bill. Thanks, everyone.